But I want to make sure that we have kind of a appreciation for the technique of logarithmic differentiation. It actually works in situations where we'd probably not go to it naturally. I've seen students, I give a problem on a test, say find the derivative, and I won't expect them to use logarithmic differentiation, and they will, and it turns out to be easier. It's the idea to exploit the properties of logarithms to make differentiation easier. That's the idea, although it sounds horrible. We want to find the derivative of y with respect to x really explicitly for this expression, and this would be awful. This is kind of one of the ones where we use the quotient rule, and inside the quotient rule we've got the product rule, the numerator, and the chain rule in the denominator, and inside the product rule, the numerator, we've got the chain rule going on some more. We don't want to do all that. So what we do is we begin by taking the natural log of both sides. Of course, we hope y is positive now in order to do this, but it's going to work out. Natural log of y equals the natural log of x squared. I'm going to write it sine x to the fourth over 4x minus 9 to the 1/3. Take the natural log of both sides. Before we take any derivatives, simplify the right-hand side as much as possible. Expand that logarithm just as much as the properties of logarithms will allow you to expand it. So on the left, we just copy and paste. On the right, the log of a quotient equals the difference of the logs. So log of the numerator minus the log of the denominator. And then the log of this product, x squared times sine of x to the fourth, is equal to the sum of the logs. So natural log of y equals natural log of x squared plus natural log of sine of x to the fourth minus, and this logarithm really is not too much more we can do except take that 1/3 out in front. So 1/3 times the natural log of the quantity 4x minus 9. And then as we did that, the 2 can come out in front, the 4 can come out in front. So natural log of y equals 2 natural log of x plus 4 natural log of sine x minus 1/3 natural log of 4x minus 9. Careful, don't want to go too far. We don't have a nice property for the log of the difference, the log of 4x minus 9. I'll sometimes see that done, but we just have to leave that log of 4x minus 9. We can't push that any farther. Now, we're in a position to take derivatives. Because, yeah, we're composing the natural log with some expressions, but it's not nearly as awful as it would have been otherwise. Because I could shrink that down a little bit. I hadn't thought of that. Let's do this. Need space. All right. So differentiate both sides with respect to x. It's going to be ddx of the natural log of y equals, I'm going to go ahead and differentiate term by term on the right-hand side, or at least write it out that way. ddx of the entire right-hand side would be ddx of 2 natural log of x plus ddx of 4 natural log of sine x plus minus ddx of 1/3 natural log of 4x minus 9. On the left, ddx of the natural log of y is the only place we really need to use implicit differentiation. But it's for that reason that we did implicit differentiation first and then did the logarithmic differentiation. ddx of the natural log of an expression is 1 over that expression times the derivative of that expression with respect to the variable, with respect to x. So 1 over y dy dx. Over here, It's all explicit. d dx of 2 natural log of x is going to be 2 times 1 over x. A little bit of chain rule. d dx of 4 natural log of sine x is going to be 4 times 1 over sine x times the derivative of sine x cosine x minus 1/3 times 1 over 4x minus 9 times the derivative of 4x minus 9. 4. So, actually a couple more steps. 1 over y dy dx equals 2 over x plus, what do you call it, 4 cotangent x? Minus 4 over 3 times the quantity 4x minus 9. I want to do two things. I want to write this so that I have dy dx all by itself on the left. So I need to multiply both sides by y. So we can do that. Maybe up here. dy dx equals y times everything we had on the right, 2 over x plus 4 cotangent x minus 4 over 3 times 4x minus 9. And if we were differentiating implicitly, this would probably be a good way to leave the final answer. But the problem really is expecting an explicit expression for the derivative, basically nothing but x's on the right-hand side. Because that's the way it was given. It was solved for y in terms of x, so we should have dy explicitly in terms of x. So one more step. Pick up the y and replace it with x squared sine to the 4th x over the cube root of 4x minus 9. So dy dx equals x squared sine to the 4th x over the cube root of 4x minus 9 times 2 over x plus 4 cotangent x minus 4 over 3 times the quantity 4x minus 9. Looks like this.